Howdy. I figured I'd make a short video on a project that I've been working on for the last couple days. This I got back into homebrew computing a little bit, and I threw this together in literally a few days. It is I call it the ASAP. Actually, you can see the name here is a little different because I changed it at the last minute. For those that don't know, SAP stands for simple as possible, but this is not a simple as possible computer. And so it would be unfit to call it a super sap. So I just call it an ASAP instead, an almost simple as possible computer. You can see it resembles, well, I would say it resembles the front panel of an Altair 8800, but Logisim is a little silly sometimes. I can't layer buttons on top of certain items, which is a real shame. Anyhow, um, so just a little demonstration of it. It's a strange little machine. It has an 8-bit address. It's a Harvard architecture, funnily enough. So it has 512 bytes of memory, but it's divided up in two. So there's 256 bytes of program memory and 256 bytes of RAM. And I figure if something's going to be this small, you don't really have to worry about having your program memory and your RAM be in the same place. So it's not. Um, so it has a 4-bit opcode asterisk, kinda. It kinda has a 4-bit opcode. This thing has a little bit more than 16 instructions. Um, I'll show you through the suite. I'll show you the layout. But ultimately, it's based around a 4-bit opcode. If I go ahead and examine uh, on 00 or on 00, I'll refer to addresses and values in hexadecimal. At location 00 in program memory, if I wanted to look at RAM, you set this high and examine, and it switches you over to RAM. Turn it off, it switches you back to program memory. Right now, I have loaded a little Fibonacci sequence program. It's not very visual right now. I plan to add more lights to show the status of the machine. That way you can get information out of it quicker. But right now this interface will have to do. I have some really, really basic functions. Examine next, examine deposit next, deposit reset, reset memory, run, and stop. Stop is more of an emergency stop thing. It's best that you set up halt in the middle of it. I'll give a rundown on the architecture in just a second. So if I give this program a little run, you can see it halts already. I wrote it so that it will start processing, and every time it's computed a step, it will halt. If I look in RAM location 0, you will see the previous iteration, and RAM location 1 shows current. And so if I go back to line, I believe it's line 5, yeah, this goes back to the add instruction. If I run it again, it goes ahead and stops. And if I go back to RAM location 0, you can see it's 1, 1 and 1. And so I'll do it one more time so you can see, give it a run. Or let's run it a couple times. So it should be at, what, 3 and 5, I think? So if I look at memory location 0 and examine it, 2 and 3. And if I examine location 1, it's 3. I'll do one more. One more. Examine and run. And then I look at memory location 0 in RAM. There we go, 3 and 5. So it's doing its thing. It's doing what it needs to. So let me go ahead and give that a good reset. It's going to look like a nightmare, but I promise it's a lot simpler than it looks. Actually, like a third of the complexity is just the panel. So this is the entire thing. This is it. Um, the entire computer has three registers, an X, a Y, and an A. The A register serves as a temporary register, as well as the result register for calculations. All calculations are done on the X and Y registers. This full ALU is able to do addition, subtraction, and or exclusive or and not logic functions, as well as a left and right rotate. Um, that's not simple as possible, but if you want to teach some very low level aspects of programming and algorithms, for example, if you wanted to use a rotation based multiplication, you could implement this on this computer. It doesn't detect negatives, so technically all the integers are unsigned, but it does have a an unconditional jump. Jump if the carry flag is set, jump if not carry, jump if 0, and jump if not 0. So if you actually disregard this section, this is just for the front panel, and this is just for the front panel, and that is every single control line in the computer. It's very, very small. The computer is basically this section right here. We have our clock module set up here, ALU and registers here. We have the memory access here, and right here is the this is just the program memory and instruction register, and all the control logic is down here. And it's divided into ICs with the machine control logic, ALU, register, load and store, jump, register, move, and panel control logic. But all of the control logic is extremely simple. That's for all the machine instructions, ALU. That's it for the load and store, the move control, and jump control. It is not a complicated computer. And another benefit is that something that I found kind of wanting on like Ben Eater's videos, the control logic is just coded into a ROM. I kind of like the hard coded approach. I just like it. In fact, the most complicated part is the panel control logic, but it's just kind of in a bunch of pieces. So I can go back here. I'm going to change something using the front panel real quick, and then I'll get into the everything, how it works. Well, not really how it works, but just the instructions it has. So if we line 4 of the Fibonacci program, if I go ahead and take a look at that, it is a 0, 1, 0, and that is the opcode for halt. I am going to go ahead and deposit here 0, 0, 0. Run on back here and run this. While I take a look, this should run on forever. Yeah, so if I go back to the layout, you can see right here it's doing its operations. Let me go ahead and pull up the instruction list. The idea here that I had was to create an almost simple as possible computer, one that has a little more functionality and a little more expandability. Now, it's still extremely limited, and you can probably only store 1 or 2 small programs in the program memory at a time. It's limited. It's really, really limited, but it's able to perform more arithmetic operations. You have more freedom with moves and stores than other more limited computers, at least that I've seen. Whenever I've seen people make computers with 4-bit opcodes, it's extremely basic. Maybe there's addition and subtraction, maybe basic move instructions. But I feel this one works all right, and technically it's not a 4-bit opcode. Each instruction, it takes up 12 bits, The top 4 is the main opcode, but the bottom 8 bits may be used interchangeably. And to illustrate that, I can pull up the instructions over here. If you take a look, there's a list of instructions here. I don't know how many it is. There are 5 machine instructions, 8 ALU instructions, handful of load and store, some moves, and jumps. So you can see with something like the addition, because all math is performed on the X and Y registers and then stored in the A register, you don't need to specify an address that you're adding to or from. You just do the thing. And so the idea here is if you look at so LXI is load X immediate, that would be opcode 2, and then you do an 8-bit number. But for the machine instructions, like no op, halt, clear flags, clear carry, and clear 0, none of those need that information. And so the middle 4 bits are interchangeable between instruction and data. And so for the moves, it may look kind of silly, like 1, 2, 4, 6, 8, and 9. It may look kind of silly. But the top 2 bits and bottom 2 bits in that middle 4-bit section are what control what registers output and which ones are set to input. So move Y to X, the 2-bit code for register Y is 1, 0, and the 2-bit code for register X is 0, 1. And so it is A for move, 9 because it is source destination, so 1, 0 to 0, 1, and then this last nibble we don't care about. That last half a byte we don't care about. And so for the jump instructions, well, they need an address, and so it's in 8 bits. There's really not too much to say about it. It's a simple design. It works very efficiently. Every instruction is only 1 line, so you don't have to worry about long instructions running. It's just, it does its thing, and I think it does it well. You can see it's kind of got a light show going on up here. I hope to make the front panel look a little more like that. I hope to write maybe a little bit of educational programs, maybe do a tutorial, I'm not sure, but I think this is something that I actually might build on a transistor level or an IC level as a personal project. I do plan to become a teacher. I feel this would be a really neat teaching tool for students. It is able to introduce basic concepts of computing, much like Ben Eater's Simple as Possible. I know he got that from there's a specific book that he mentioned, and I've read through it before, and so I've borrowed on some of those ideas. I've expanded in a couple areas to make it more comprehensive, but overall, that's the whole thing. Let me know what you think. If you have Logisim, I'll post a link for you to use the circuit, maybe a Google Drive link in the comments. I'll have to see, get feedback on it. But that's about it. I'm going to go ahead and program a little program off the top of my head. But thank you very much for watching. Let me know what you think. So let's do a little program. I'm going to go ahead and stop this so you can see what the interface is like. I can reset. It's pretty simple to work with this. So let's say that I want to write a program where I don't know. I said I'd come up with one off the top of my head, and now here I am stuck. Let's say you have a program that adds the 2 locations in memory. let's say that location 0 plus location 1 stored in location 2. So the first things first is we need to, I'm going to have this on my right side. I'll bring it over and back so you can see. So our first things first, we want to examine, and so we are sitting here. And if I go ahead and examine next, examine next, examine next, you can see I have a program in here. If I go back to 0, I can go ahead and reset memory. And if I go ahead and examine again, and then go through, examine next, you have to click twice because the way it works is it examines and then increases the program counter. And then it examines and increases the program counter. So when you're at 0 and I click examine next, it's examining and increasing, but it's showing the program counter as it is. If I hit it again, it's doing the same thing. It just looks like it has a little lag. So it's no bug, it's just an unintended feature. It doesn't cause any harm, but I digress. I shouldn't digress. First things first, we need to select our 2 memory addresses that we're loading in from. Let's say just 0 and 1, add them together, put that into 2. This should be a really, really simple program. So we would have to do load x with 0. And we can see over here, load x is 4, followed by data. So 4 in our opcode is up here. And then we want to say 0, 0. So 4, 0, 0, because we are loading x with address 0. I'm going to go ahead and click deposit next. Deposit next does exam next. It does something very similar to examine next. It deposits, it increases the counter. So when I click deposit next, we can now see what instruction is at the 0th position, the 0th address. So next, I need to do load y. Load y is right here, 6 with data. So 6, and then this is going to be address 1. And so deposit next. And we can see 601 stored at address 1. Next, we need to add. So that is pretty simple. The arithmetic instructions all start with 1, and add is the 0th instruction, so it is going to be 1, 0, 0. And it doesn't matter what you put here. You can put this if you wanted. I'll put it so you can see that it doesn't affect anything, but ultimately, it's not going to do anything. So we have our add, and last but not least, we need to store back into location 2 and then halt. So our store A is 9, so we need 9, 0, 2, deposit next, and then last but not least, we need to go ahead and halt. All machine instructions start with 0, specify with 1, and deposit. And so now we have 0, 1, 0 at 4. Now, I could go ahead and run the program, bring it exam 0, and I can run the program. All right, it's run. Well, let's see what the result is at, oh, actually, I did reset the memory. So if I just examine the RAM at location 2, oh, well, isn't that something? See, I thought that I had reset the memory. What's it showing at location 1? Location 0. 0, 1, and 2. Now that's really interesting. Here, let me examine this. Examine next. So 4, 0, 0, 6, 0, 1. Okay, 1. 1, 0, F. Let me try setting this to 1, 0, 0. Maybe there's something going on. Let me deposit that there. Examine next. then 0, 1, 0. Go back here, examine, RAM 2, examine, showing 2. Looks like we are having technical difficulties, and I do not know why. Here, let's go look at the ASAP layout. So it's running in here, and it looks like it's showing 0 in memory. I'm not quite sure why it's doing that. I'm going to pause here. I'll be right back. So I immediately caught that after I paused it. I apparently cannot even read my own computer. The data line was empty. If I examine RAM location 0, 1, and 2, the data line is the top one. The address line is the bottom. I might flip them to avoid confusion. So it did exactly what it's supposed to. So let's go ahead and put a value in 1 and a value in 2. So I'm going to examine RAM location 0. I'm going to go ahead and put 1 and 1. So I'm going to deposit here at 0, and then I'm going to deposit at 1. So now I'm deposited. Go back to exam and run my calculation, and then examine memory location 0. There we go. Memory location 1 in RAM, showing a 1. Memory location 2 is showing a 0 for some reason. Unless I'm not storing my X back. Looks like I'm having more. Oh, I'm not storing my X back. I did make a mistake. So let me examine. So we have 400. We have 601. 10F, and then 0, 100. Okay. Oh, I overwrote my previous thing. Okay. So line 3 is 100. So I need to go ahead and put in my store X, which my store X is 9902 deposit. There we go. Now I can examine run. There we are. So now if I examine RAM location 2, we're showing a 2. Happy days. This shows you how new this is. I still have to reference stuff to program it. Usually with my projects I get to a point where I just think like it and I'm set, but you can see here. Anyway, brief demonstration. I plan to do better documentation so everyone can see everything better. Goodness gracious. My apologies. I'm gonna have to close that out here. Thank you very much for watching this far. If you kept going for see me and my blunders. I'd love feedback. If you are interested in homebrew computing, if you have something you think that it will improve this, or something that, like a piece of a functionality that doesn't seem right, let me know, and I'll get back to you. So thank you very much for watching. Have a good night.